Welcome to Mr. Powers Teaches Math. I'm just doing math, general math. I don't know. Independent, dependent events. It sounds like statistics. Probability. I'm sure they're related. And I want to talk about independent and dependent events today. Last time we just talked about real quickly about what probability is. What is it? Definition. We talked about theoretical and experimental probability. There they are. And so now we're going to deal with, well, what if we want to find the probability of two things happening, one right after another or at the same time, which effectively are the same thing? So whether you want to think of this, then this, or them happening at the same time, it's the same. Don't worry about it, okay? Kind of. You'll see. So, when we're doing that, we got to consider and worry about whether or not the first event will affect the outcome of the second event. If the first event, whatever we end up doing, will affect the outcome of the second event, well, then those two events are dependent, or the second one relies on the first. So then we get dependent events, okay? If, on the other hand, one thing doesn't affect the other, then they're independent events. And so this is a thing that's very important to keep track of unless we're dealing with very, very, very large numbers. Then we can finagle it and just treat everything like it's independent. Sometimes we do that because it's close enough then. But anyway, for our purposes right now, we are not going to do that. We're going to definitely want to know the difference. So dependent events would be if I were to say, draw a card, pick a card out of a deck of cards, right? Draw a card, and I'm looking for, let's say, a jack. Let's say that, a jack. And then draw another card from the same deck. I'm not putting that card back. So I keep this, I draw a card out, it's out, and then draw for a red card. Those two things are going to be very much dependent. If I want to know the probability of first getting a jack, then a red, well, those are dependent events, because what if the jack was a red card? Or even if the jack wasn't a red card, right? There's less cards in the deck after I get the jack out. So those are dependent events. One thing affects the other. However, if I was going to say do the same thing here, I was going to first, see here, draw a card looking for a jack. Oh, and then, whoop, here we go. Put this up here. If I was going to draw a card looking for a jack, okay, and then flip a coin for heads. Well, what I do on the coin has nothing to do with the deck of cards that I did for the first event. So those two things are independent. Okay, so there's a couple examples for you. Now, when we're computing the union of two events, or something like what I was just saying, it's like, what's the probability of this happening than this? That's kind of like saying, or, oh no, wait. No. Sorry. So now something a little different. So we talk about independent, dependent events. Now the union of events. So now what if I want to know the probability of this happening or this happening? This or this. And that's what this union means. This symbol here is a union symbol. And think of it like an or. So this, when you see probability of E union F, where E and F are two different events. And they could be the two events I was talking about right up here. What's probability I draw a jack or I get heads, right? That could be our E and F. Okay? Or in the first one, first example, again, this could be the same as probability E or F. Okay? Because an or is like a union. So we want to know if this or this happens. What we do is we end up adding each of those probabilities up. That's how it works. Now, then we got this little thing here. We do have to do one thing afterwards. We can't just add up both those probabilities, because what if these are dependent? In other words, what if, like right here, right? I draw a jack and it's a red jack. Well, I don't want to get all the ways I can get a red jack and draw for a red card. Those can happen at the same time. So if I just add these probabilities, what I did was I added an outcome twice, kind of. I added two probabilities. I double counted is what happens. And so we got to take that back away. And so we got to take away the probability that E and F happen at the same time. That's what this means, is what happen. Take away all the ways that E and F happen at the same time. I got to take that out. And so that's what this is. And when you see intersect, that's this upside down U. That means intersect. That's like an and. P of E and F. So, and I love to do this with, it's like, would you like super salad at the restaurant? It's like, yes, I would like one. Which one? Oh, well, soup, right? But if I say I want soup and salad, it'd be no, I don't. I only want soup. So there's my fun little example for the way we treat ands and or. It's a little different, okay? Now let's go ahead and do an example. Let's do an example. I have an example problem here. Let's take a look at it. Hold on. All right, here we go. There are 22 students in a math class. 6 of the students are on the school basketball team. The teacher draws a name out of a hat to select a student at random to hand out supplies and then puts the name back. Next, the teacher draws another name to select a student to pass back graded projects. Complete the sentences below. Express probabilities as fractions. Okay. So first thing you might want to think about is, are these events independent? Since we're drawing a name out of a hat, and then we are putting the name back and then drawing a name out of a hat again, one event's not going to affect the outcome of the other because we're putting that paper back in there. So it doesn't matter which one happens first, right? The probabilities for each event are going to be the same. One event doesn't affect the other. So these are independent for sure. Okay, so something to think about. Now let's go ahead and answer these out. So the probability of the first student chosen on the school basketball team is. So how many are on the school basketball team is 6. What? Why are you doing that? 6. And there were 22 students altogether. All right. Assuming the first student chosen was on the basketball team, the probability that the second student chosen is also on the school basketball team is, well, it's the same thing, right? 6 out of 22. In fact, you could choose the same student twice. Right? Didn't say you couldn't. So it's definitely they're independent events. So the probabilities are equal, is what we'd say here, because the teacher does replace the first name. So they are independent events. All right. Let's see if I can find an example with dependent events. See if I can find that. Okay, one more example. Penelope chooses a card from a 52 card deck and keeps it. She keeps it. It does not go back in. Then Anna chooses a card from the deck. Okay, so then Penelope chooses a card, then Anna chooses a card. Complete sentences below express probabilities as fractions. The probability that Penelope chooses a queen is, well, how many queens are in the deck? 4. Okay, so 4 out of 52 cards total. The probability Anna chooses a queen is, well, that one's actually really tough to do. So I wonder how this delta math is figuring this out, because if she picks a queen, assuming she gets a queen, if she does get a queen, it's 3 out of 51. There's 3 queens left, and there's 51 cards left in the deck. But if she doesn't get a queen here, then there's still 4 queens, but still only 51 cards in the deck. So the point is, these are not the same probability, no matter how we're thinking about it. These are different. These are dependent events. So let's go ahead and jump back into Delta Math here and type those in, see what it says. 4 out of 52. Let's go, I'm going to go with the 3 out of 51, just for fun here. We'll do the assumption that Penelope gets a queen. So the probabilities are not equal because Penelope did not replace the first card. It did not go back in the deck. These are dependent events. All right. It says I got it right, so that's funny. Okay, so second draw. So we are going to make that assumption on our homework, is that she did get one of those. In the second draw, since Anna did not put it back and it was a queen, there's one less card, so 51 cards total, and number of queens is 3. So there you go. So we did it great. And there you go. So there's a little quick example of independent and dependent events. We did not do the or yet the union type stuff. So no, we'll worry about that later. So until next time, enjoy doing math.